So thank you for that. I have that you are fun after break. So now I switch to another part, but very connected to the first part. So we have addressed many points in the first presentation, like the coastal hazards, as flooding, erosions, and the components importance that should be considered for such coastal hazards. So now we will go to the climate, and we will look for the connection, the physical connection between climate and hazards. So if I have a storm today affecting my coast, is it related to Nina now and all the climate oscillation or not? And if so, how is this connection, and how can you use the climate oscillations to understand the local dynamics? So we are speaking about a downscaling from the global scale to the local scale. Okay? So I show here, like, when we speak about physical drivers, we have many phenomena, okay, many mechanisms, including atmospheric pressure fields. We have what? Have atmospheric. We have atmospheric pressure fields, sea pressures, temperatures, the effect of tides, high tides, spring tides, neap tides, a lot of mechanisms, okay? And all the hazards inducing the coastal problems, okay, are induced by one mechanism or the combination between different mechanisms. We speak about compound or cascading hazards, natural hazards. So we have all the hazards occurring at the same time or very close in the time. And here, like natural hazards are interdisciplinary by nature. Like we have many disciplines, and they are very, they occur in cascading or in a cumulative way. Okay, so for example, I can take an example. When we have heat waves in US or Canada, we have storms and colds in Europe, and we can have many other examples. And I will present you a very early example in July 2021. Occurred in Canada, US, and North Africa. So, like the distribution of temperature, for example, anomalies in July, we have, as I told you, like heat waves in some environment, in some places in the world, and devastating floodings in other sites in the world. So, extreme events between different regions in the world are we have discrepancies, we have different extremes occurring in cascading. So the previous works have demonstrated that the occurrence of extreme events and their interdisciplinary are related to some global mechanisms, basically atmospheric circulation to the Gulf Stream. So what's happened? Like the Gulf Stream, it's currents between ensuring the stability between the South America and North Europe, and this current has or is taken some problems in time in changing climates, basically the weakness of its trajectory and the variation of this trajectory in the space. Okay, so the weakness, the speed is not the same, and the trajectory. So, and just to add this information here, and if you have some people from America Latina, of course, they know this, that this Gulf Stream, or the weakness, the changes of the dynamics of this Gulf Stream is responsible on the increasing temperature in the tropical tropical zones, and this decreasing is responsible on this weakness, but also on the instabilities between linear climate oscillations and the increasing of the frequency of extremes and storms that we have demonstrated in the time that the frequency is increasing. It depends on the site as well. So weakness of the stream with convoluted pattern, like all the pattern and the trajectory is changing in time. Like we are not the same changes between heat and cold water masses in the space, and that could be explained by this instability. So, as I discussed in the first part of this seminar, that all processes or mechanisms from at the scale of the extremes to the scale of climate oscillations, we have different time scales from long term, from the diurnal or extremes, seasonal, interannuals, decadal, and long term, like we look at climate change. And some scales are well known and others are not really solved. So here the challenges to understand the interaction between the different scales as addressed at the beginning. So as well, we have in the spatial scale the global ones, the regional, and the local ones. For example, if I am interested to the coast in Asturias and to look for this coast, so I cannot look on what's happened in Asturias. I have to look on all the regional scales, and then from the regional scales, it will be important for me, useful to understand the behavior and the changes of all hydrodynamics that would be used in an input for the local scales. So we see like we have many interactions. So we speak about weather and climate. You know the difference. So weather, it's more local changes at short time scales. And when we speak about climate, it's the long-term averages, okay? And it's the weather averages over several decades. So we have like differences in the time scales. And like the weather is a very small component from the climate. So I take some examples, whether like some what I say, extremes related to weather, related to weather extremes, like tornadoes, for example, extreme events like climate related to climate, darkness, increasing of temperatures. So we have different extremes. Some of them are more related to the global dynamics and the climate, and others are related to the weather. Okay, so extremes or events are caused by natural cycles. We have many changes in the different cycles, in the different climate oscillations, Nino, now South Atlantic Oscillation and other, and they are also immediately influenced by high pressure systems. So we have also a combination between different oscillations. That we will see in this part. So I will start from one real example. Okay, so in July 2021, okay, between 14 and 15, we had a very alarming events. I remember that I was in Netherlands there because I lived there, and we received some alert by phone. We have to leave your home because we have a very like a devastating flooding. So this day, okay, we had flooding between the north of Netherlands, Belgium, Germany, and the north of France. So like 4 countries are affected by this flood. So what's happened? And I remember that we have 240 deaths and a lot of European insurers, like a lot of money and budgets invested by European insurers. So it was one of the most expensive events for insurers from 1991. So what's happened here? Like I told you, like from between Monday and Thursday, July 2021, and here we have a very serious phenomena during 24 hours. So we have extreme rainfall, okay, and a very important fluvial activities. And all you see here in animations, okay? And we have an extreme, you see right here, it's a very, the red points, huh? In 2021, just, okay, it's very, it's like unusual values. And all that activities has affected the discharge in the watershed and the fluvial activities and induced all the flooding. But this system is connected to the coastal area, okay, in Belgium, in the north of France, and we have connections between like fluvial activities and like high energetic waves. And it was the flooding in coastal area were enhanced in this time. So here we have also other mudslides. Yeah, and other phenomena. Okay, so we have cascading, many extremes occurring in cascading. So with the other colleagues, I remember from Aachen University, we have looked for this phenomena, and we have looked for all the mechanisms. So I have just participated with them in this. So they have assessed the following: that we have heavy precipitations, flooding in Western Alps, and this precipitation is basically started from Baltic Sea. Anomalies, warm sea surface temperature. We have like heavy heat waves in Baltic seas, and then these such heat waves or increasing temperatures has in very like mountain area has induced slow moving, long-lived and low-pressure systems, bringing a lot of moisture and over Belgium, Germany, and Baltic Sea. So then we have like some cooling and rainfall generations, and really very severe rainfall, and it all led to extreme precipitation anomalies. That was very extreme. And when we saw what's happened before this period, like 15 July 2021, we saw that we have heat waves in Canada, US, and Ireland. As we see, you see the red points here, that we have really heat waves. So, see here, like we have the red points, we have really extremes, and the discrepancies of extremes, like before all the extreme or cold period in Europe, in Western Europe, in North Europe, and Canada, US, we have really heat waves. So what's happening? So discrepancies between two extremes, cold and extreme rainfall, fluvial, flooding, and heat waves in other parts. And here it's basically linked to some other climate mechanisms at the global scales. So when we have done some investigations, we have looked for the trajectory of Gulf Stream has been changed, and due to the weakness of these currents and the difference on the trajectory, as you can see here, the normal trajectory, and then the trajectory, it's very like with big dips and swings between the north and the south, So it's like it's a modification of the trajectory. So the communication of the changes between cold and hot water masses or bodies has been changed, and that's why we have instability. And this instability has been responsible on cold air from poles clashing against hot air from tropics. So we see like an example where one extreme event, very local in space and in time, and this extreme event, very local, has been connected to a very global mechanisms of the in the atmospheric circulations. So here, these extreme events has been linked to weakened winds, dangerous weathers, prolonged extremes, disasters, and every others, basically controlled by these changes of the global stream. So now we So now what we have done here, we have decided to look for all time series. And how can we connect all the variability of like whatever the variable, sea levels, rainfalls, discharge, winds, and we have looked for this variability in time and the connection with climate oscillation. So what we have done here, we have taken normally here in the channel. So we have taken many like different stations along the channel, Brest, Cherbourg, Dakar, for example, and we have applied a non-stationary continuous wavelet transform. It's like Fourier transform, but it's more adequate to assess the non-stationary behavior in the time series. So what we see here, it's very simple. I will explain you the diagrams. There are a lot of colors. It's wonderful, but you have to understand behind this that we have in time all the time series. You see, like all the data, and in the y-axis we have like all the cyclicities, all the frequencies that we can extract from the time series. So we see like in Brest we have like I don't remember, maybe more than 14 years, and no more. Maybe we have like more than 14 years, and we have applied the continuous wavelets to look for the different frequencies, as you can see here, the difference of colors, and the different frequencies or cyclicities controlling the variation of sea levels. I explain just one example, these examples, and we see that we have different cyclicities, like at the scale of annual scales, like we have a lot of variability at annual scales, others interannual scales between 2, 4, 5, 8 years, and other is decadal scales, it's more than 10 years. I suppose, I am not sure that we have learned about the cycle of 6 years in everything, in magnetism, in many like variabilities in our natural systems. We have like some cyclicities that could be observed each 6 years, and this cyclicity, it's highlighted in our data, our local data, like sea levels. It's like between 5 and 8 years, but it's basically 6 years, and it depends. It's a range of cyclicities. So then, what we have done here, we have reconstructed the variability of each cycles, okay, and we have tried, to correlate it, before this, we have tried to look for the different scales. We have like decadal scales. We see like the red diagram, the Gaussian that have like cyclicities are decadal each 12 years, between 5 and 16 years. We have others like between interannual scales, and we have seasonal scales. We see like the colors, like decadal scales, okay, very low frequencies, variabilities. We have then interannual scales, okay, between less than 10 years, between 2 and 8 years, and others, it's basically related to the annual seasonal variability. So we have a lot of components, a lot of frequencies in one time series, and we have to understand the mechanism, the physical mechanism responsible on each frequencies. Why we know this? Because it's a way to understand all the systems and to estimate all the systems. That's our approach, our research that we have done. Like we have decomposed the time series to many spectral approaches, and each spectral approach is explained by one physical mechanism. And I will show this now. So it's an applications I have taken. It's one publication in 2022. I have taken all the sun estuaries in France, in the northern side of France, from the upper stream to the downstream, and we have looked for all the stations along the systems. And I have here we have looked for the contribution of the fluvial parts and the marine parts, and then at large scale the impact of atmospheric circulations or climate oscillations in the variability. So we have the following. So first of all, okay, we have taken the signal, the red one you see, and during all the time, okay. It's one example in the downstream. I cannot show everything, okay, all the signals, but it's one signals in the downstream. And we have looked for all the storms produced between 1964 and 2010, okay? You see like the color boxes or the extremes, like A1, A2 until A26, okay? And we have looked for the behavior of the systems of the time series at the different frequencies related to the extreme. So how this signal, okay, or the different frequencies or of the sea level is changing according to the storms. Okay, so here what we have demonstrated that we have a lot of storms, and each storm has its return period, 2 years, 10 years, 20 years, okay? And when we have some storms with a very high return period, like 20 years, these storms is more manifested at low frequencies, like decadal frequencies. And when we have small storms with very small return period, like it's very frequent storms, like you can see them each year, are not really manifested or correlated to atmospheric circulation. So the biggest storms with high return periods, like storm, we can observe it each 10 years or 20 years, such very big storms are correlated to all the atmospheric circulations, pole stream, climate oscillation, and all these atmospheric mechanisms. And that we have seen there, you know, in the estuary, the same. We have like reported all the extremes, you know, the color bars. And we saw that many extremes, many big extremes are manifested at low frequencies, okay? And such extremes are really very significant compared to others. So, like one extremes produced at the local scale, it's very related to all the global circulation. So, what is the whole message behind this? It's crucial. That's okay. If we know that climate oscillations contribute to extremes, so we can use climate oscillations as covariables, as parameters that could be considered in our models to estimate extremes. That we have done in our reports. Yeah. So we have connected the scales from global scales, regional scales, and local scales. Okay, we take the global atmospheric circulations, regional, for example, the Europe, and local, in my case, for example, Seine estuary in France and all the English, okay, between France and UK. So we have demonstrated that many climate mechanisms operating in the channel, like the variability, the long-term variability of many variables, waves, sea levels, discharge, precipitations, no, I speak just about marine variables, are monitored, are controlled by climate oscillations, sea level pressures, zonal winds, the winds at a certain level, and North Atlantic oscillations, NOWs, okay? So here, what we have done, we have decomposed the signal, okay? I take the search as a variable. I have decomposed my search to many frequencies from D1 to D7, okay? From high frequencies to low frequencies. High frequencies like variabilities, very high variabilities, high frequencies, okay? And low frequencies, it's very slow variabilities, like trans to stationary behavior. The high frequencies are very non-stationary behavior. So it's very different and the estimation is different. So we have decomposed all the signals to different composites, and we have done the same for atmospheric field or sea level pressure. And then we have connected one by one, like for each frequency, we have connected the local variable of search to the atmospheric circulations. And we saw, it's a very interesting paper, this one, like we saw that the connection between the local scale search, for example, okay, in this case, and the atmospheric circulations is different at depending on the scale. It's not constant, it's not stationary. It's changing according to time. So we have some, you see like the colors, the distribution of colors. To be I try to be simple and to be very simple and fast to know. Like you see like the distribution of colors between the red and blue ones. We have different composites, you see, and each composite is one scale: 2.1 years, 4 years, 7.8, 15.6, and 21.3. So we have different scale, that's one, and we have different distribution of colors because the connections between the variability of the local signal and the atmospheric circulation is different. So what's happening? What is my home method again? Like I can use these connections to develop models for estimating the variability of my local variables. What we have done here. So we have this connection, I explain again. And we have demonstrated in this part that such variation are related to the shift in the graph stream between 6 and 8 years. I said before that 6 years is very famous in many variable systems in the world. Okay, and it's really as well. It's really correlated to the weakening trend of the graph stream variations. So what we have done here, we have used this information, very useful information, to develop our model in order to estimate waves, currents, and all the values. I take here the case of surges. We have estimated storm surges. So what we have done, we have used the different climate oscillations as co-variables in our GOV models, generalized extreme values, to include the effects of such climate oscillation in the estimation of the surge. But here it's more complicated. Why? Because the hazards are not separately or compound. So, for example, in English Channel, we have compound flooding induced by surges and waves. You see here? So we have like looked for estimated the compound flooding related to both variables. And we see like to have some extremes with assigned return period, 2, 5, 10, until. So we have some curves, and we can like use this graph to understand like for a return period of one value of waves and one value of surge, we have this combination. Like we need these to include them in our numerical models to simulate our compound flooding and to know when we have this value of waves, we have the silent or the related surge. It's like the varied densities between waves and surge to understand the return levels assigned or associated to the compound flood. Then we have moved here, we move here, we have used the climate oscillations to understand, to estimate like the hydrodynamic variables. Then we move here, and we will look for the effects of climate oscillations on the pitch, on the erosion. It's a work done since 2 years, I guess, for wind pitches, Narabin, with some colleagues from Australia, in Spain, in Bulgaria, in Barcelona, in Normandy, and we have looked for the different oscillations and how such oscillations have impacted the beach. Okay, so I take here many examples like Narabin, Bulgaria, Etretat, in Normandy, and we have used here like the continuous wavelets. Like as I told you, we have the time and we have the frequency of the period. And it depends on the length. The time series, of course, we have a lot of data, but in Arabic we have a lot of data. So we see like we have different frequencies, like the erosions or the variability of the shoreline is monitored by different frequencies or time scales. Like we have some variability at decadal scales between 8 and 12 years, at between 3 and 6 years, annual and seasonal ones, So we have different variabilities when monitored at different time scales, and it's the same for all beaches. So the same, but you saw like you see like we haven't the same frequencies here because we haven't a lot of data. Here we stop until seasonal ones here because it's the data. Okay. So and then we have connected all our frequencies to different storms. For example, I see like here we have Gareth storms produced in 2019 in Normandy. Okay, so we see like red patterns here, and these red patterns, it's a lot of variabilities, and this lot of these significant variabilities, power or variance, is related to these storms. So here I will take an example. So I have reconstructed all the frequencies. 1 year, I take some examples, 1 year, 6 months, 3 months, 1 month, and I will have reported all the extreme events. It's formed by color, okay, or Arabic. And then we have like connected all the variability of the shoreline to the different reported storms, and we see, in this case, we have looked for the longshore and the cross-shore variation, like rotation and translation of the beach, and we look at, we have some storms more correlated with cross-shore and others more correlated with longshore variabilities. But the main home message here that we have connections between storms and the different frequencies. Okay, that's the first step. And then what we have done, we have correlated the longshore and the cross-shore. The longshore is the rotation of the beach in the longshore direction, and we have correlated this with different climate oscillations. These of South Atlantic, South Oscillation Index, sorry, and then video like the decadal. I have like another decadal. Pacific decadal oscillations. Okay, so we have connected this, and we see like at low frequencies, the variation of the beach are correlated. Okay, but we have in phase or in out of phase. It depends in the phase. Okay, but we have like here we have out of phase. We have in phase, out of phase, in phase. It depends, and we have a lag time between the different correlations. So here it's an example to show you that we have correlations between the local variability of the beach morphological parts and the climate oscillations. So we have strong connections, and then we have put like reported all Nino and Nina events. We see like in blue Nina events, in green Nino events, and we have looked like where we have significant shoreline changes between Nino and Nina. So for scales higher than 8 years, we have some activities, very specific activities of the beach, like there are very important rotation, clockwise rotations in this direction of the clockwise rotation, yeah. And for scales smaller or lower than 8 years, we have other activities of the shoreline. So we see here like such phases of Nino controlling the activity of the beach along the beach, longshore or rotation, say you symbol, okay, and the cross-shore one, but the cross-shore one I haven't presented it. But basically here is the longshore activities related to the climate oscillation. So climate oscillations is like the global scales. We are doing this scanning to look for its connections at local variables, at hydrodynamics and morphological. So this part of climate oscillations, and in our work now, but with all colleagues from my research units and university and all the colleagues from LargeScaleAtmosphericCirculationand as well, we are thinking about how or what is the contributions of each climate oscillations to put it in the estimation or estimating the variable or the local variability of the variables or sea levels or waves. And that's very important because all climate oscillation can contribute in the variability of the signal, but the contribution is different. For example, the SLP can have a dominant contributions and the NAV can have another less significant contribution. So it depends on the scale, but it depends as well on the site where we are doing this. So here the home message in this part of climate downscaling that climates are very important to be considered in our model and for long-term estimation of the variability of the hydrodynamics in coastal in oceans, but it could be as well for continental and fluvial seas. So, okay, so now we have addressed two crucial points. The first one, coastal hazards, their dynamics, how they have burned and have affected the coast, how the coast can resist or not, can be resilient or not to such hazards, and then how such hazards, in the second part of this seminar, how such hazards are connected to climate oscillation and atmospheric circulations. That's from the connection between extremes, local extremes, and long-term oscillation at Gulf Stream and others. So, okay, if we know this, we can simulate our numerical simulation or deep learning simulation, and we can estimate the response of our systems to all such hazards. And when we assess the consequence or the impacts of all hazards, this is why we can, and this time we can propose or develop our solutions. What are the solutions used to protect my systems for this impact, for this impact assigned to one extreme or to several extremes? So we speak about nature-based solutions to build the resilience of coasts and to enhance the sustainability of coastal area. Okay, so I know that how we can take actions to overcome such problems of impacts, natural impacts of hazards in a coastal area. So how can we build resilience? I think that most of you, with Mario, you are doing many solutions as like green hybrid solutions or gray solutions. So we have different solutions. We have gray solutions, like we construct dikes, we take actions by adding another components to our system, but anthropogenic components. We have other solutions like based on nature. We set these green infrastructures or green solutions by developing parks, by developing wetlands, vegetated wetlands, by developing many other like fixation of dunes and other. We will take some examples. And finally, because it's very hard to develop nature-based solutions, we develop hybrid solutions. Like we take the nature to deploy some solutions, but we include other gray solutions to be able to maintain the solution in time, since the monitoring of nature-based solution is not so easy. But we will see what are the different. So I see gray solutions, green solutions, and hybrid solutions. So here we need an integrative planification based on adaptive management. A management, but that could be adaptive, which we can adapt to this management. We can deploy a management, but not adaptive for people for certain parts. So it's a problem. So we have to select the most adequate tool with adaptive version. So what is our rule here? We assess the risks. We identify the risk. We identify the solutions, and we put the solutions. With the solution, we deploy the solutions. We take the actions, okay? And once the action is done, is taken, we cannot leave and forget it. No, we have to measure the effectiveness of all solutions, to look for the efficiency of all solutions in time. It's very important, this point. And that's why I told you in the first slide that it's hard to revive sometimes. For some solution, it's hard to follow or to monitor all these green solutions. So here the connection between two parts that I told you in the first. I said in the first part, digital twins model or the models, but calculated by all data, improved, enhanced, like data, satellites, in-situ measurements to reduce the uncertainties, and nature-based solutions. So to propose all solutions, I need accurate results. I need to understand exactly, but the best way, the risks, and to do this, the digital twins model, the use of these models is very important to have a very good overview about the risks. That's risk that could be a background to deploy or to propose or develop my solutions, like adaptation strategies. So I will take an example to explain you what are basically and what are the main actions related to nature-based solutions. Some of them has already taken in Normandy. For example, in Nature-BasedSolutions and we have taken some actions. Okay, so I will start from a system. A coastal community. We have different components: physical, ecological components, economic components, socio-economic components, social ones, and we have the interaction between all components. So what's happened? That all components are interacting with the life. That's normal. But this interaction is more and more complicated in a changing climate. So that will increase the hazard. So we see in the second diagram, we have all building flood, okay? So we have such components will reduce the resilience and increase the vulnerability of the systems. So when the vulnerability of the system is increased, we have overwash, flooded area, many other problems. Okay? So what is the solution here? So solutions. Start by, I have taken some 3 examples. We will just follow the red line, the red rectangle. Okay? So house remodeling or setbacks. Okay? So some houses are really constructed close to the coast, and we have 6 problems in South France, in Spain, this is a crucial point. If we have a lot of building close to the coast, you know that we have a minimum distance from the coastline to all constructions, at least 200, and maybe it's more for other countries like Portugal and other. Okay, so we have to respect this distance, and unfortunately, in many coastal areas is not respected. So one of solutions. For example, we have electricity in Normandy. All constructions, we have to take off all constructions. We have to put them far from the coast. Second one, the blue part, green parks. Like we have to implement more restorations. Okay, green parks, vegetated area, and yeah, we use the nature systems to put more vegetations. Okay. Green solutions, and then some construction of bridge. You see here we have bridge on the bridge to reduce all the impacts like flooding. Okay, so we have here some hybrid solution, not really green. Okay, because we have all the constructions, but some solutions to face to our to protect our coast and face to our hazards. So I can mention some examples of nature-based solutions: urban wetlands, coastal ones, vegetations, coastal reefs, use of vegetation for the fixation of sediments or dunes, inland wetlands, floodplains, mangroves. It's the same concept. Green solutions like use restorations, aquacultures. optimization of the land use, like we cannot concentrate all the land use in one part. We have to distribute all our urban constructions and land use to balance the density of such use around the coast. It's very important. So, for example, I will take an example in Netherlands. My colleagues from that we have done, building the resilience. So, in this system, they have started from the baseline, from this part, okay? And they have included some nature inclusive scenarios, and they have changed the distribution of all land use, like grouping all urban areas, developing many agroecological space developments, increasing the biodiversity. Sorry. So they have changed the distribution of construction around the area to enhance these protections. And then another excellent example in another examples in in France is an excellent example. It's like they have used or have developed vegetated for dune stabilizations. And here I will go so fast. So they have done some boxes, and such boxes they have put a lot of algs, okay, a lot of algs and others, the algox, that's why we name this algo box. And then such algs will liberate some enzymes, and the enzymes will help the vegetation to be enhanced and developed. And the vegetation will increase the fixation of sediments. And then they have observed, they have in the beginning a very significant problem of soil humidity, and after 5 years, they really obtained the solution was effective, and the retreat was less important than before. So I will be very quick. So here, for our nature-based solution, we have to interact all components, ecosystems, societal, the well-being. So we need here and the economic parts, okay? Because maybe we can implement some nature-based solution, but from an economical point of view, it's not feasible. It's not feasible for the government and for other, like the responsible. So we have to look for an integrated planification based on an adaptive management for coastal resilience and sustainability. So we know we have to integrate all the components to look for the best solution, most adequate one for our systems. Yeah, I can. It's okay. So just one. Just here. Okay, we seek science, we speak, we try to do many research action, that's fantastic. But our relationship with stakeholders, our engagement, our scientific engagement with all stakeholders, it's crucial. Without this, we cannot do really. I will just mention some things. Our effective and proactive communication, dissemination of our results, adaptation strategies. We have to develop interacting approach management with citizen-centered visions for these communications, the implementation of video camera to snap. How I think that you learn about this. Okay, it's very important to involve all people in each action of surveying, the shoreline, and finally maybe the implementation of flood warning systems, like some systems. Warning systems to be informed when we have some problems, alerts, or others. So finally, I will just finalize by this, like at the end, this resilience, it's a balance between facing coastal risks, implementing nature-based solutions, and taking the actions to manage. So this is the science, fantastic, but you need to take decisions, like decision making on coastal risk management is very important. And to take such decisions is the role of the government, is the role of our stakeholders, our manager, coastal manager to do it. And fortunately, I hope that the case, everywhere, and our coastal managers are based on our scientific and research results to take the best coastal or the best decision for protecting the coast. So it's my our message of this seminar. Coastal resilience, it's a balance between reducing the exposure and the vulnerability of the coast and developing adaptation strategies or adaptive strategies by making the most adequate decisions for protecting our system. And that's it. And thank you very much.